Hello everyone and welcome to the video for section 8.4 dealing with trigonometric substitution. So what's the objectives for this lesson are: number one, use trigonometric substitution to solve an integral, and number two, to use integrals to model and solve real life applications. Now the issue that comes into place here, when you use trig substitution, it is going to be a complete change of variable. Now, when we've changed variables in the past, you've changed it from, you've used like a u, okay, when we use a u substitution to do the integration, like we did in 8.1. What we're going to do here, we're going to, these integrals involve square roots, and we're going to go through, do a substitution, and it's going to be going through and where we're going to end up dealing with an integral of trig functions. And it's no accident that this section here follows 8.3, where we looked at the trig integrals, so those procedures. Okay, let's go take a look at this. So what we have here is we're going to be using integrals, and they're going to the integrants where they're going to involve square roots, and the roots are going to be in one of these three forms: the square root of a squared minus u squared, square root of a squared plus u squared, or the square root of u squared minus a squared. Now, based on that, we're going to make a substitution, and that substitution is going to be one that it's going to allow us to simplify this expression. So when we're working with integrals in this form, we're going to end up using this fact right here, that version of the Pythagorean identity, that cosine squared theta is 1 minus sine squared theta. So you can kind of see that form, the 1 minus sine squared, kind of that form right in here. Okay. When we're dealing with the square root of a squared plus u squared, we're going to use this version of a Pythagorean identity, that secant squared is 1 plus tangent squared. And if we're going to use this version, we're going to use an alternate version of the one that we just used, that tangent squared is equal to secant squared minus 1. Okay, let's take a look at this procedure. So when we're working on these, we're going to really be dealing with three cases. Case one, what I have in white there, is where for integrals involving where we have the square root of a squared minus u squared, we're going to let a or u equal a sine theta. So I'm going to replace that u with a sine theta. So when I do that, I'll have a squared minus a squared sine squared theta. Okay, and when I simplify that square root, then by that, using the Pythagorean identity and everything, it's going to come out to be a cosine theta. Now looking at case two. In case two, we're going to involve the square root of a squared plus u squared. And so in that situation, we're going to replace that u. Now remember, u in all three cases, u is some function of x. U could just be x itself. Okay? But it is going to be something involving x. So u, we're going to, whatever's being squared right there, we're going to let that equal a tangent theta. And when I plug that in and do the simplification, the square root itself is going to become a secant theta. And in case three, where I have the square root of u squared minus a squared, I'm going to let u equal a secant theta, and then I'll have the square root of u squared minus a squared is a tangent theta. Now these are the three cases. Okay, the actual procedure when you're going through and doing these problems is going to be the same. You're going to identify what the substitution is. You're going to have to think about what that square root is going to become. But remember, this is an integral, and it's a complete change of variable. And that also means we're going to have to find out what dx is equal to. Okay? Because we're going to go through, change this up so it's completely an integral involving theta. Let's take a look at an example. So for this particular example, what we have here is the integral of x cubed over the square root of 16 minus x squared dx. Okay, so because looking at that integral, or the square root, that's in the form of a squared minus u squared. U is equal to x. A would be 4. So I'm going to let my u, which is x, equal 4 sine theta. By plugging that 4 sine theta in for x and simplifying it, that square root, the square root of 16 minus x squared, is going to become 4 cosine theta. Now the other thing I have to deal with is this part right here, the dx. So I know since x equals 4 sine theta, I know dx is going to be 4 cosine theta. I forgot the d theta. So now with that, I am now ready to go and set up that integral. So in this case, I'm going to replace x with 4 sine theta. I'm going to replace the square root with 4 cosine theta, and I'm going to replace the dx with 4 cosine theta d theta. So this is going to become the integral of 4 sine theta, that thing cubed, over 4 cosine theta times 4 cosine theta d theta. Now the nice thing I can do at this point is I can go and reduce this, and I notice that the 4 cosine thetas will drop off, and so my integral is now equal to the integral of the 4 sine theta cubed, so that's going to be 64 sine cubed theta d theta. So looking at that, that reminds me of my trig integrals. And so I'm going to go through from here. We can start taking that. I'm going to pull the 64 out times the integral of. Now if you remember, when we had the odd power on sine, I'd pull out one factor of sine. So I'd have sine squared times sine theta d theta. And I'm going to replace the sine squared with 1 minus cosine squared, the Pythagorean identity. So that's going to be 64 times the integral of 1 minus cosine squared theta times sine theta d theta. And now the nice thing here is I can do a u substitution. So on this particular problem now, I'm going to let u equal cosine theta. Du is going to be negative sine theta d theta. I have the sine theta, I don't have the negative, so I'll put a negative and a negative. So when I make my substitution, this is now going to be negative 64 times the integral of 1 minus u squared. And then that's going to be du. And so when I do that, that's going to be negative 64 times u minus 1/3 u cubed plus c, or I'm going to get negative 64 times, replacing u with cosine, it's going to be cosine theta minus 1/3 cosine cubed theta plus c. Now at this point, you might be thinking, oh cool, we're done. No, you're not. The issue is this. Our original problem is in terms of x. We need to get this in terms of x now. Okay, now this is what I know. I know that x equals 4 sine theta. So from that, I know that sine theta is x divided by 4. Because I can just go through divide both sides by 4. I'll get sine theta is x over 4. Same thing here. I know that the square root of 16 minus x squared equals 4 cosine theta. So therefore, cosine theta is the square root of 16 minus x squared over 4. So I can go through, set this up. I'm going to go through, make that substitution. I'm going to replace the cosine thetas with the square root of 16 minus x squared over 4. So in that case, I will now get negative 64 times the square root of 16 minus x squared over 4 minus 1/3 times the square root of 16 minus x squared over 4, that thing to the third power, plus c. And that will end up being my final answer on this problem. Okay, I can simplify it. I could cube that, distribute the negative 64, but the end result is that would be enough right there. Negative 64 times that quantity, that you have to put the bracket there, of the square root of 16 minus x squared over 4 minus 1/3 times that square root of 16 minus x squared over 4, that thing cubed, and then don't forget the plus c at the end. Okay, take a minute, make sure you're comfortable with all these calculations, everything we did in this problem, and once you are, let's go on to the next example. Now this particular example, example 2 here, is an example of an application problem in this, when you have this. And so what's going to happen here, and I've kind of already done all the work, so it's kind of talking it through. I want to find the arc length of y equals 1/2 x squared on the interval from 0 to 1. Now this is a nice, easy problem to work with, because I know, if you recall, arc length is equal to this. The integral from a to b of the square root of 1 plus the derivative of f, that thing squared, and then dx. So on this particular problem, y, or f of x, is 1/2 x squared, so f prime of x is just x. And so for this particular problem, the s, my arc length, is just equal to the integral from 0 to 1 of the square root of 1 plus x squared dx. So in this case now, this one is all set to be a case 2. This is where you have the tangent. So I will let x equal tangent of theta. And then therefore the square root of 1 plus x squared is going to be secant theta. And dx then is going to be secant cubed theta d theta. So when I do my substitution, now on this particular problem, I did a complete change of variable. I even changed the limits of integration. Okay. So s was equal to the integral from 0 to pi over 4. Now I got those because when x is 0, so if 0 equals the tangent of theta, theta is going to be 0 itself as well. And when x is equal to 1, so I have 1 equals tangent of theta, the inverse tangent of 1 is pi over 4, and so we get the pi over 4 there. And so doing my substitution, I have the integral from 0 to pi over 4 of secant of theta, that's my square root, times dx, which is secant squared theta d theta, which that simplifies here. And this problem right here should look somewhat familiar to you, because we did this one when we worked with integration by parts. We did the integral of secant cubed. We didn't have the limits of integration, we just had the secant cubed. And what we found is that the antiderivative of that, you can look back in your notes and see the whole process there. But the antiderivative of that was 1/2 times secant theta tan theta plus the natural log of secant theta plus tangent theta. And I'm going to evaluate that from 0 to pi over 4. So now what I'm going to do is I'm going to plug pi over 4 in for theta and all the thetas. So secant of pi over 4 is square root of 2. Tangent of pi over 4 is 1. And so when I do that, I get 1/2 times the square root of 2 times 1 plus the natural log of square root of 2 plus 1. Now, you'll notice I didn't do the minus 0. What happens when I plug in 0? When I plug in 0, the tangent of 0 is 0. So this will be 0. And here, the secant of 0 is 1. So I'll get the natural log of 1, which is 0. So when I plug in 0, this is just going to be 1/2 times 0. So it's not even going to come into play. So I'm going to end up with the exact answer for the length of the arc is 1/2 times the quantity of the square root 2 plus the natural log of square root 2 plus 1. And that, if you plug that into your calculator, will come out to be about equal to 1.148. So this now concludes the video on the trig substitution. We did an example of the two of case 1 and case 2 in this video. Now on this problem here, if you did not want to go and make those changes, you do not have to. You can always go back to x, so you'd have that one additional step where you went to this point, then you'd have to go through, use the fact that tangent of theta is x and the secant of theta is the square root of 1 plus x squared, and replace the secants with the square root of 1 plus x squared, and the tangent of theta, replace that with x. You'll get that with x, and then just do the fundamental theorem of calculus with the 1 and 0. So this does conclude it. I hope this that you're comfortable with this right now. We'll take a look. Remind me in class to show you, make sure you're comfortable with that. The fact that what the square roots are equal to. If you want, we can go through that. But with that, we are finished with this one, and enjoy the rest of your day, and we'll see you in class.